Hello everyone. I hope everyone is okay. Today we'll be going over through the problem. Find all possible recipes from given supplies. This is a medium problem on LEETCODE. First, we'll read the problem description. The problem description states that there are n different recipes, and you are given there is we are given a string array called recipes, which is this one. Secondly, we are also given a 2D string array ingredients to build a single recipe to build this ith recipe. We will need these ingredients. Okay, this you can read this here. Uh, for example, if here you can see, and we are also given an array called supplies. These are the basic supplies we are given when we start building the recipe, when we start cooking. These are the basic supplies we are giving from the start. Okay. The note there is also a note given. Note that two recipes may contain each other in the ingredients. Like for example, like here, bread. There are two recipes which we need to create. First one is bread. Second one is sandwich. Bread needs yeast and flour, and sandwich needs bread. First, we will need to create build. We will need to create a bread. Then using that bread we can create a sandwich here. For example, and meat is present in the supply, so there is this sandwich can be built. You can say return the output. Order doesn't matter. Okay. Note that the two recipes may contain each other as in their ingredients. I'll just explain how. Basically, you can solve this problem using many as analyzing this as a you can say as a graph problem. The intuition behind recognizing this as a graph problem is quite simple. Everyone if you know graph theory, if you know some of the graph theory, you can solve this problem using topological sort, or a simple cycle direction problem, simple cycle direction with some cycle direction. Okay. These are the two ways you can solve this problem. Like for example, bread has two ingredients. For example, yeast and flour. Yeast has no requirements because it is basically present in the, you can say, supplies. So supplies are originally available to us. This for example is the like is for example, this is the thing I'm talking about. If for example, we will build an agency list, for example, like this. We will first go over to the bread needs yeast. We will go to the yeast has no requirements and is present in supplies. So that means yeast can be built. Yeast can be built. Yeast can be created, for example. Another for same is the case with this. There are two cases. First we will check, for example, first we will check if an ingredient is supplies. Second, if else ingredient not in supplies but can be created using other ingredients. This is the main crux of the problem. For example, we will need DFS function, which will check if an ingredient is available in supplies. Then there is no need for, you can say, uh, another, and there is no need for another, you can say, the recursive call. If the ingredient is not available in the ingredient is not available in supplies, we can you can say use a recursive function to check if the ingredient can be made, or else something like something that. I'll just start the code here. I hope everything is understood by now. This is my first video, so try to just you can say cooperate with me. Basically, this is a. I'll just again go again through the problem. This is a basically simply a graph problem. The intuition behind recognizing the graph problem is simple. For the topological sort part of the problem, you can basically check if, for example, if you can start from the, you can say, I'll just go over this through the code. There are three problem parts of the problem. First is building an adjacency list. Second is the DFS function. The third is the third is the building is the third is the, you can say, calling the DFS function. These are the basic problems. We will first initialize some variables. There is a res and something like called adj. Res is the output array. Result is the output array, and adj, it is an adjacency, you can say, list. It's a default dictionary of type list. Then we will build the adjacency list, like for example here, for recipe recipe for recipe ingredients in zip recipes and something like this. For now we will know zip basically, but zip basically, you can say, you zip basically what it does is, you will get the bread, and the first, basically it, you can say, it iterates with the two arrays, you can say the given two arrays at the same time, the bread and the recipes and the recipes and ingredients, you can say, array. For for ingredient for ingredient in ingredients, adj recipe dot append ingredient. I'll just show you the output here, so you'll get to know how the functions, you can say, essentially is built. I'll just like I mentioned before, this is the bread needs two things: yeast and flour. Now we will be first we will start the calling the DFS function. We will go over the recipes array. For recipe in recipes, if recipe in supplies, if the recipe is present in supplies, then there is no need for, you can say, then there is no need to call the DFX function. You can simply append into the, you can say, append in the recipe, something like this. Else else now, in the else case, the recipe is not present in supplies, so we will need to, you can say, call the DFX function to check if the to check if the ingredients of a specific recipe are present in the, you can say, present in the supplies, or they can be created from other ingredients, other ingredients. First, like this: seed, if not DFS, recipe sim 16. Now, if DFS returns a false, it basically false, for false in this case means that the recipe can be built, a recipe can be created. So we will do this. something like this. Recipe. Also, we will also add this in the created recipe into the supplies, because this is a simply an optimization technique. Because if for example if we have created like here, first we will if first we will check if the bread can be created. The bread can obviously be created because we have yeast and flour. In the next recipe, for example, in sandwich, we will also need a bread. So instead of again checking the bread can be created, we will put this bread into the supplies means that these are available for us. So this reduces the, you can say, an recursive calling the DFS function again. In the sandwich case, this will go here. Basically making the bread again is basically a useless thing for us. And in the end, we will return simply the res. Now the main thing is left, the calling the DFS function. One more thing is red left. I have used this supplies as a set. So set basically increases reduces the access complexity. Instead of searching in a list is O of O of n, and searching in a set is basically O of one. So I'll just convert this supplies into a set. So this we are searching here like this. Though if to reduce this complexity, I'll just something like this. Supplies set supplies. Okay. DFS function, same thing with recipes. This is not needed, but I'll just do this. Okay. Now we will build the DFS function. Def DFS node scene scn scene scn scene. Okay, something like that. For nay in adj, something like that. Okay. For all the neighbors of the you can say current bread. In this case, this will come here. No, the node would be bread, for example, and its neighbors would be yeast and flour. If neighbors not in scene, that means the current neighbor of the, you can say not neighbors, you can say child neighbors basically. If the neighbor of the current, you can say, node in the graph is not seen, we will call our DFS function here, like something like this. Net scene, and we pass the you can say set for the. We will also need to check for the cycle detection. For example, if for example I'll just explain here. For example, if if bread needs yeast, and okay, the bread needs yeast to be created, and for example, and yeast needs bread to be created. This is neighboring scene. This return true. That means return true. And C scene node false. Now will for example, if this false means that I have just inverted the function. DS function will that re- uh, return true means not possible, false means possible. Okay, this is that. Next thing is this. We need to check if what does the recursive function last if last recursive call return to us. If there's a true, we can return a true. If this is a true, we can return a true. And second thing would be, for example, here we need to check if neighbor is present in supplies. We need we need not to go for the rest of the you can say we need not to, you can say, basically call the DFS function again, because this is present. We need not to check again for the, you can say, supplies. This is basically an optimization technique. The code would work without this line, but this is a good optimization technique. And the last thing that remains is that, for example, I'll explain. I'll basically just explain here. For example, um, bread, yeast, yeast, flour, and in supplies we only have flour. So the bread needs yeast and flour, but in supplies we have only a flour. So in this case, the bread cannot be built. So in order to put this in condition in our code, we will need to put a, you can say, base case here. You will need to put a base case here. That means if not ADJ of node, that ADJ node and node not in supplies, node in supplies, return false, return true, sorry. Okay, that means if not ADJ means that, for example, this in this case means yeast has no requirements. Yeast needs nothing. So so in the agency list, the yeast will be something like this, something like this. So that means if not ADJ, if for example, the ingredient has no requirements, and it is also present in, it is also present in not in, it is also not present in supplies. That means it is also not present. That means that means the current ingredient, the current recipe cannot be built. So this will return true. I hope everything is done till now. I'll just move these lines. Okay, this is the agency list we are building. This is the DFS function. This is the just the we are calling DFS function and putting the, you can say, building the output array. This is the base case for checking if the everything is present in the ingredients present in the, you can say, supplies set. We are using two sets. We are using two sets to basically check for the cycle. This is an optimization technique. This is okay. This should work. I'll just try to run the code. I'll just try again for multiple test cases. I hope this works. I'll just try to submit the code.